All right, quiz 4, key, going through these problems. So the first one is lithium aluminum hydride, which is a really reactive H- source, hydride source. A couple things. You need to do the first step completely before you do the second step. So here you have two things. You have an ester and an aldehyde. And the aldehyde here is more reactive than the ester. So that's actually the first thing that reacts. So that reacts. So once that reacts, you make a tetrahedral intermediate, but there's no good leaving groups. So another H- is an excess, and also it's H4. So there's 4 H- there. You react with the ester, make a tetrahedral intermediate, add in. But now you have a good leaving group, so you do an elimination. Get another aldehyde. H- reacts, get another tetrahedral intermediate. And then, since there's no more good leaving groups, the last step is everybody gets protonated, and that makes this tetraol. Biggest things people make mistakes. They try to use the H+, not just at the end. They try to use it throughout. Just wait till the end. And they don't number their atoms, and they lose track of what's going on here, where things are at. So for number 2, we have an oxidation, and it's chromium. It's CrO4H2, so it's a strong oxidizer, but it doesn't really matter in this case. It's we go from a secondary alcohol to a ketone, so there's just one H removing. And we also could have used PCC to do this, but you don't know the mechanism with PCC. So with this one, you have 3 things in the mixture. You have your alcohol, the chromium, and H+. And the chromium, the oxygen and chromium actually grabs the H+, that makes it more reactive. Think of it like a carbonyl. The oxygen then is the nucleophile, adds in. We do a proton transfer because the best leaving group is the thing we just added. So we do a proton transfer. Now we have water as a leaving group. So the electrons come down. Now this is a little different. You're going to make H+ as a catalyst, so that H that was on the carbon attached to the oxygen needs to go. So those electrons go there, makes a pi bond right there. Electrons in the chromium oxygen bond go to the chromium, and the water leaves. So you have the chromium with a lone pair and the OH there. You've made the pi bond, you've regenerated water, and you've also regenerated the catalyst there. All right, so the last one here, mechanism and products, so the intermediate. So if you see magnesium with 2 electrons, that you should be thinking, I'm going to make a Grignard. And the way you do that with these single-headed arrows, right? So the carbon-bromine bond, the magnesium comes in between it, essentially, right? 2 electrons in a bond. These are single-headed arrows, 1 electron. So they come together to form a bond, right? 1 electron each, 2 bonds. And what that causes is the carbon that was delta plus now becomes delta minus, or even just a negative charge. And so those electrons then react with electrophiles. So it's a nucleophile. It's a basic nucleophile. So then I have it reacting with an epoxide. So then you got to know something about epoxides, and where, if you have an unsymmetrical epoxide, where do under basic conditions, where do things add? And they add in the less substituted because of sterics. So it's essentially an SN2 reaction. And that's shown here. You get the O minus. And now here, instead of having H+, which you usually have, where you just protonate, I added just another electrophile in. And we just did another SN2. And that added there. The stereochemistry is important. Wedges and hatches don't change. But you are making stereocenters here as well.